Storage of your data is one of the most important things in computing. Be it your collection of photos, videos, important documents, or whatever. You want to be able to store all of these things reliably and safely. Now, back in the day, I think most of us relied on just having a single disk to store everything on, and maybe we'd then take backups of that every now and again. And that is okay, but your data is only as good as the last backup that you took. Anything beyond there has now been lost if your disk fails. A better way is to use an array of disks all working together with your data spread across them, so that if any single disk fails, everything keeps on working. Now previously on a Raspberry Pi this was quite difficult to do because the I/O was quite limited. However, with the Raspberry Pi 5 and the introduction of the PCI Express socket, things have changed and now we can build ourselves a reliable disk array. Let me show you how. Hello once again, Pi geeks and techno nerds all around the world. My name's Jeff and I'm an IT professional who's been in the industry for over 30 years. I've been using Raspberry Pi since they first came out, and I love finding or coming across new ways to make use of them, and I want to share that with you here. If you like what you see on this channel, please hit that thumbs up button, subscribe if you want to see more, and hit that notification bell so you can be told when I put a new video out. Also, let me know in the comments about any projects that you've taken on with your Raspberry Pis, and any suggestions that you have for projects for me to do in the future. In a recent video, I took you through how you can connect PCI Express devices to a Raspberry Pi 5, and I tried out a variety of cards. However, when I was putting everything away after that video, I chanced upon another card that was lurking in the back of a cupboard. It was a SATA controller card that could be used to attach conventional hard disks into a computer. And that got me thinking, could I make use of that to then create a fully featured NAS out of a Raspberry Pi 5? And that's exactly what I'm going to do here. So first off, let's take a look at all the kit that we need to put it together. Now the first thing that you need for this project is obviously the Raspberry Pi itself. Now here, just like in my prior video, I've connected the Pi NVMe base onto the Raspberry Pi 5. Normally, the purpose of this is to allow an M.2 SSD to be connected onto your Pi. However, in this case, I've flipped the base round so it actually sits on top of the Raspberry Pi 5, and then I've connected an adapter that turns the M.2 socket into a normal PCI Express socket. This then allows me to connect any PCI Express card onto my Pi 5. I also have a 32GB SanDisk microSD card plugged in that I use to store the operating system. The next thing you need is the SATA controller card itself. Now this one has got 4 ports, allowing me to connect 4 SATA hard drives into my Raspberry Pi. Now for 3 of these ports, I'm going to be connecting these 3 hard drives, and these are going to form my resilient data storage array. Now here, I've used 3 Western Digital 2TB hard drives from their Red range. These are designed for NAS usage and to run 24/7. However, don't feel you've got to use something like this. You could use any disks you like, but just bear in mind they really do need to be the same size. You can technically use ones that are different sizes, and I'll show you how to work around that later. However, you will be limited as to whichever one is smallest, and that will ultimately govern the capacity of your array. So it's best to get 3 that are the same. The 4th drive I'm going to connect, I'm going to use for backups. Now this is deliberately sized as twice the size of the smallest hard drive that I'm using in my data array. And again, the reasons for this will become clear later. The next thing is to provide power to all of my disks, and to do that I'm going to be making use of this. It's a Pico power supply. Now you can use these to actually power PCs. This is a 160 watt version. Now you can see that all of its circuitry is exposed there, and you may feel this is really dangerous. However, the great thing about Pico power supplies is that everything is low voltage. They take in a 12 volt power supply, and then makes available both 12 volt and 5 volt supplies to all of our devices. Since everything is low voltage, then it's all perfectly safe to handle. So please don't worry about the fact there is no case around this. Now, the only problem with these kind of PC style power supplies is that by default they're switched off. Just like with your home PC, nothing happens until you press the power button on the front of your case. Now, we don't have that in this situation, so we've got to simulate it. And that's what this little device does. It's called an ATX power starter, and it connects onto the ATX power connector. And then on the rear of it, it connects these two pins together. Now, one of these corresponds to the power button connector and the other one to ground. So what it means is that it behaves just like if you pressed and held down the power button on your PC. So effectively, as soon as we plug in our Pico power supply, it will immediately start providing power to all of our hard drives. Now, conventional spinning hard disks do get quite hot, and so I wanted to get some fans to provide cooling for this. Now, these are three 80mm fans, and they're not the most premium make in the world, but I was able to get them quite cheaply from AliExpress, and they do work really well. Now, the Pico power supply doesn't have any fan headers on it, so I've had to get this adapter cable that allows you to plug into a regular Molex connector on one end, and then it's got 5 connectors on the other end to allow you to hook up all of the different fans. Now, the PCI Express adapter on the Raspberry Pi also needs power, and the cable that comes with this also uses a Molex connector. So I've had to get a splitter here to allow me to connect both the PCI Express adapter and the adapter that will provide power to all of the fans. The other issue I have with power is that the Pico power supply only has a single SATA power output. So I've had to get this splitter cable that allows me to connect to that and then split that to provide power to all of my hard disks. Now, I mentioned earlier that the Pico power supply takes a 12-volt input, and that's what this power brick provides. This is a 12-volt 150-watt power supply, so it can provide plenty of current to feed everything that we have here. Now, rather than having all of this just sitting on a desk as a sprawling mess, I thought it was a good idea to have some kind of enclosure. Now, rather than buying a regular PC case, it would have been quite a lot of money, but just over £11, I was able to buy this. It's an acrylic hard drive enclosure. Now, normally, this would allow you to connect up to 10 hard drives to it. In our case, we're only going to connect 4, but then I also want some space to allow our Raspberry Pi and its SATA controller card to sit in here, and the Pico power supply. The little brackets in the middle allow each of the 3 fans to be connected, so they will sit on the front of the enclosure. Now, this is actually all clear acrylic, but you can see it's still got the covers on. And that can only mean one thing. It's time for a peeling montage. Now we've got our enclosure sorted out, the other thing I need is something to act as a shelf for my Raspberry Pi, and also another to act as a shelf for the Pico power supply. So I picked up a couple of these 2.5-inch to 3.5-inch disc adapters. Now, I picked these up on Amazon. They were probably a little bit more than I really wanted to spend on them, and you may be able to find something a lot cheaper on AliExpress, so do shop around. But what was really useful with these particular ones was that they had this fairly solid metal plate surface to them. Now, this allowed me to drill some extra holes into it and then mount my Raspberry Pi straight on top of it. So I could then put this in the enclosure and everything would be held really securely. And once all of this is put together, it looks something like this. I'm really happy with the end results. It looks a little bit chaotic, but also quite industrial and fairly cyberpunk. So I'm really happy with the end result. But now we've got all of the hardware configured, let's go and take a look at configuring the operating system and actually get these hard drives set up. Now, the first thing you're going to want to do here is install Raspberry Pi OS onto the micro SD card. Now, I used Raspberry Pi Imager for this in order to install Raspberry Pi OS 64-bit Lite version. If you've never installed Raspberry Pi OS before and you want more information on how to do this, take a look at my video right here and it will take you through the entire process. However, when you're all finished, you'll be able to SSH onto your Raspberry Pi and you'll be able to get onto a terminal window just like this. Now in my prior video, where I connected other PCI Express devices onto my Raspberry Pi, I explained what kind of speeds you can expect to experience on your Raspberry Pi. And that's shown in this table here. There are two different generations of PCI Express that are supported on the Pi5, Generation 2 and Generation 3. Now a BY1 socket for a Generation 2 socket will have throughput of 4 gigabits per second. However, for Generation 3, it can provide 7.88 gigabits per second. So for this particular project, we definitely want to enable that. In order to do that, you want to go back to your terminal and you need to edit the file /boot/config.txt. If you go all the way to the bottom of this file, then there are two parameters that you need to provide. The first one, dt_param equals PCI EX1, actually activates the PCI Express interface on the Pi5. The second parameter, dt_param equals PCI EX1_gen equals 3, forces the PCI Express socket into Generation 3 mode. And that way we can get the highest throughput we possibly can. Once you've added those lines into the config.txt file, just save it out and then reboot. Now our Pi is rebooted, we should now be able to see the disks. Let's go and take a look. Firstly, let's make sure we can see the SATA controller. And indeed, we can see the SATA controller there and drivers have been loaded. This is a great start. Now let's see if we can see the disks. And yes, we can see SDA, SDB, SDC and SDD. We can see the first three are our data disks, as their size is shown as 1.8 terabytes, which is the amount of usable space on our 2 terabyte hard drives. SDD is our backup disk, shown as 3.6 terabytes, which is the usable space out of a 4 terabyte drive. Now we're going to build a RAID array on our data disks. And it's important that you understand what I mean by a RAID array. So let's go and take a look at that. Now the easiest way to set up a load of storage is to just connect each independent disk onto your machine, mount them separately and then store files on them. The problem of course is that if you lose any one of those disks, then all of the files that you had on it will be lost and you won't be able to get them back again. So if we look at the maximum capacity across all of your disks, it's whatever they all add up to. However, your maximum drive loss before you start losing data is 0. The moment you lose any disk at all, you lose data and you can't get it back. So it's better if you can connect disks together in the form of an array. And a technology that allows this is called RAID. Now RAID operates at a bunch of different levels. So let's go and take a look at each of them. The first of these is RAID 0. Now this doesn't actually help a lot with resilience, but it does help with performance. In this case, if you've got a single file, then parts of it will be spread across all of your disks. So in this case, each of the 3 green blobs that you can see represent one file. Now what happens is, as you have something that's trying to read that file, as you're reading the data from the first disk, it'll be in the background preparing the second disk so that all of its heads are in exactly the right place for you to then read the data for the next section of that file. So you can seamlessly just move on to it. And then it'll do exactly the same with the third part of the file that sits on the third disk. And this will just keep on going, preparing the next disk in the chain or looping back round to the first disk again to get that ready to read the next part of the file. Now if you lose any one of these disks, you're effectively in the same position as you were before, in that you can't access anything anymore. Because your data is spread across all of the disks, it means you've lost everything. So with RAID 0, your maximum capacity is again the sum of all of the disks that you have, and again the maximum number of drives you can lose before you lose data is 0. You lose one, you've lost everything. However, you do get better read performance out of RAID 0. But because of the lack of resilience, it's very rarely used as its own thing. The next level is RAID 1, and this is referred to as mirroring. With this system, as soon as you write to one of the disks, its data is also written to the second disk. and they're kept exactly in step with each other. And what this means is that if you lose one of the disks, you haven't lost any data at all. You can still read and write to the second disk with absolutely no problem. And then you can replace the failed disk, resynchronize everything, and then just keep on going. So you won't necessarily have any downtime whatsoever. Now this has a trade-off in capacity, because the maximum capacity of your array is half the sum of all of the disks, because half of your disks are effectively mirror copies of the other half. But in this system, you can lose half of your disks without losing any data, although that does assume that the disks that you lose aren't both sides of a mirror. If you lose both sides of a mirror, you have no way forward. There's then what's called RAID 1 plus 0, sometimes called 0 plus 1 or RAID 10. And this is a combination of RAID 0 and RAID 1. So here we've got 3 disks on the top, and these are configured as RAID 0, so our file is spread across each of the 3 disks. However, in order to provide redundancy to that, we've then got a mirror pair for each of the disks on the bottom. And so what this means is if we lose any given disk, the array can keep on going because it can use its mirrored pair to still provide service. So here, once again, the maximum capacity is half the sum of all of our disks. And again, you can lose up to half of your disks, assuming you don't lose both sides of a mirror. And you also get the better read performance that you would have got from RAID 0. A sort of compromise to this is what's called RAID 5. Now with RAID 5, when you write to it, parts of your files are spread across all of your disks. And there's then what's called parity information added as well. Now this is kind of like checksumming in a way, but it also provides a way to construct data that's missing. And by spreading all of this data around and making copies of it and having this parity information that again is spread across all 3 disks, what it means is if you lose any disk in your array, your service can actually keep on running with absolutely no problem. And again, you can swap out the failed disk, bring in a new one, resynchronize everything, and just carry on. Now with RAID 5, the maximum capacity you have is the capacity of your total disks minus the capacity of one disk. This is because all of that parity information takes up the equivalent of one disk. Now if you lose any single drive in your RAID 5 array, everything is fine and you can keep on going. If you lose 2 drives or more, then you will lose absolutely everything. So in effect, the more drives you have, in terms of capacity, RAID 5 is more and more and more efficient, because the overall capacity you have is always the sum of all of your disks minus the capacity of one disk, and you get all of the benefits of the better read performance. Now in this project, I'm going to be setting up my 3 data disks as a RAID 5 array. So out of those 3, if I lose any single disk, I'll still be absolutely fine. And I'm also going to keep a separate backup on the other hard drive, just to provide even more redundancy. But this is why my backup drive was sized at 4 terabytes. I've got 3 2 terabyte drives, so my maximum data capacity is 4 terabytes. 6 terabytes across all of my data disks, minus the capacity of one disk. So here, I should have a pretty good and pretty reliable system. Now in order to set up our RAID 5 array on our data disks, I need to install some software first. The first thing to install is the Logical Volume Manager, or LVM. And I can install that with this command here. Now the reason I'm installing the Logical Volume Manager is because of the issue whereby your disks may not be exactly the same size as each other. To get around this, what I like to do is create logical volumes on each of the disks. I can then ensure that they are exactly the same size as each other, even if the physical disks are slightly different. So when I was talking about the disks earlier, and I was saying that you don't necessarily need to buy disks that are identical. For the purpose of building a RAID array, they do need to be the same size. So as long as your disks are roughly the same size, that's fine. You've just got to size all of them based upon the smallest one. Now this may mean that you're wasting a bit of space on the larger hard drives, but as long as they're not wildly different from each other, then that's not really a big inefficiency. In my case, all of the drives are the same size, but I'm going to go through this process anyway. Firstly, I need to add each of the drives into the system so it's aware of them. I do that with this command here. So now the logical volume manager is aware of them, I now need to create what are called volume groups for each of the disks. Now this was designed as another way to aggregate disks together, but you don't get a lot of resilience from it, so I need to create a different volume group for each disk, and then I'm going to use a different system to bind everything. I'm also going to create a volume group for the backup disk as well. Now they're all created, I now need to create the logical volumes themselves. Now I need to provide sizing information here, and this is where you need to check the size of each of your disks. If I run VG display against my first data disk, you can see that its complete size is 476,931 extents. And it's this extents figure that is really important. You then need to compare that to the other disks that you have. In my case, they're all identical, so everything is fine. If you have any differences between your disks, make note of the smallest number and then always use that in this next step. This has created a logical volume called LV_data01 within that volume group on the first disk, and its size is exactly 476,931 extents, which is equivalent to roughly 1.8 terabytes. Now this will have created a new device under /dev called VG_data01/LV_data01. So now let's repeat this for the other disks. Now I've done this for the data disks, but I need to now create a logical volume for my backup disk. That's going to be a lot bigger, so let's check the maximum size of that with VG display. And you can see this is 953861, so I can create a logical volume up to that size. So now I have all of my logical volumes. I know all the ones for data are exactly the same size, and then I have also one for my backup. Now I can go ahead and create my RAID 5 volume. But for this, I need a command called mdadm, and I can install that like this. Now I can create my RAID 5 array, and I do that with this command here. The first parameter defines what I want to call my RAID array. In this case, I'm calling it MD127. I then specify what RAID level I want to create, in this case 5. The RAID devices argument specifies how many devices there will be in the array, in this case 3. And then I finally provide all of the device IDs for my data disks. This has now created my array, but it will actually take some time to build, as it has to synchronize metadata about the array across all the disks. You can see the status of this with the /proc/md stat file. Here, you can see it's reporting that 2 out of 3 disks are up, and the entire synchronization process should take about another 222 minutes, or roughly speaking 4 hours. Now I should still be able to use the system in this time, but performance will certainly be compromised. But let's see if I can create a file system on this array. Okay, we now have a file system on our RAID array, and so I should now be able to mount it. Firstly, I'll make a directory to mount it into. Oh, actually, in my case, I created this on my Pi earlier, but that's the command I used to do it. However, I should now be able to mount my RAID 5 volume onto here. And if I run df-k, I should now be able to see that my 4TB volume is now mounted there. Next, I want to change the ownership of that directory so that my Pi user can write into it. And let's just make sure that I can. That's worked successfully, and if I do a directory listing of that directory, there you can see our test.txt file. I'll just clean that up again now. The next thing I want to do for this is set up some software that I can use to actually share this directory out to other computers on the network. This software is called Samba, and I can install it with this. I then have to create a configuration file for Samba. And if I go right to the very bottom of the file, I can see this. Now I just need to create a new section for my NAS. The first line here just gives a general description of what the volume is that you're sharing. The second parameter is a path to the file system that you're going to be sharing out. The third parameter says that you can just browse this file system. The next parameter says that it's not read-only. And the final parameter says that you have to be logged in order to be able to see the share. Now I have this, I just have to save it out. The next thing I need to do is define a user that is allowed to use the share. In this case, I'm just going to make the Pi user capable of doing that. I can do that with this command here. It asks me for a password to set for the sharing. This is actually a different password to the one that's normally used for the Pi user. However, I'm going to make it the same in this case as Raspberry. I then need to restart two services for all of this to take effect. The first of these is SMB, and this is the service that actually takes care of all the file sharing itself. The other one is NMB, and this takes care of advertising the share across your network. Now we've done all of this, technically your NAS is ready to go. However, its performance will be severely limited by that initialization process. So I want to wait for that to complete. I can monitor its status with this command. And this will update every 2 seconds. So now I'm just going to wait for this to complete and come back in about 4 hours. As you can see, our array is now entirely built and we have these 3 U's here showing that each of our disks is up. Now it's all complete, we can take a look at the performance of our array. In order to do that, I'm just going to use our normal disk test. And here you can see it's able to read at 270 megabytes a second. This is roughly speaking about 2.2 gigabits a second. So it's really great performance. Now, of course, your NAS is going to be capped not by this read performance, but by the speed of the network, given that the Pi5 has got a gigabit network interface. So you're never going to be able to read more than a gigabit. But this is great because it means that the disks themselves are not the bottleneck to your system. It's the networking instead. But now let's go and take a look at a couple of different systems actually accessing our NAS and see what performance they get. In order to test the performance of our system, I'll need a test file that I can use. I'm going to create this here. It's just going to create a file that's 1 gigabyte in size, consisting of nothing but random characters. Now we have this, we can use it to check out the performance of our NAS. The first test I'm going to run here is on a Windows box. On the right hand side, I've mounted our NAS as the X drive, and I've just done that using the normal Windows sharing mechanism. On the left, I've got a local directory on my Windows box with the test file that we generated. So if I just drag that across the NAS and then copy it, you can see that the performance we're getting is roughly speaking about 105, 108, 110 megabytes per second. And that works out pretty much to gigabit speed. So that's really cool. So now let's try copying it back again and see what performance we get there. And again, it's coming down at really very much full speed, so gigabit kind of speeds. And this is great because it means that we're limited by our network bandwidth rather than the disk performance. The second test I'm going to do here is on my Linux box. And I'm going to do effectively the same thing. I've already mounted the NAS into a directory called /mnt/NAS test. And what I'm going to do here is remove the test.dat file, then use SSH to actually create it on the NAS, copy it over onto the local box, and then copy it back again. Now, if we're getting anything near about gigabit performance, each of the transfers should take, roughly speaking, 9.2, 9.3 seconds. So let's see what performance we get here. And yes, as you can see, against the real time that's been recorded here, when we copied from the NAS to local, it took 9.17 seconds. And then copying from local to the NAS storage took 9.2 seconds. So again, we're getting very, very close to gigabit performance. And this is really excellent. We can look here at the power that the NAS is consuming from the main power supply. And as you can see, it's only about 21 watts. This is really, really cool. And just shows how efficient the Pi NAS is. Now, if I bring in the terminal that we were using before and I repeat that copy, you can see that the power will jump up a little bit, but not very much. Even when it was at its highest load, it only made it to about 26, 27 watts. So the system really is very, very power efficient. And whilst I can't say for sure, I'd certainly hazard a guess that if you compared this to a mini PC, it would probably work out more power efficient than that. The only other thing I really wanted to mention in terms of performance is that with all of the fans going, this is really quite noisy. Here you can see I was running my noise meter and it recorded something close to about 50 decibels. Now, in terms of background noise, that can get really annoying, especially where it's quite a high-pitched whine. But a lot of this is generated by the fact that the fans are going at full speed all the time because they've got nothing to slow them down. And what you can do here is buy something like this, where you could attach the power connector that is driving all three of the fans into this, and then you could use the control to slow the fans down, and that would quieten things down quite dramatically. Now, I haven't bothered to do that here because I've got the NAS kind of tucked away somewhere, so it's not really bothering me. But if you did have it close to you, then I would recommend picking up something like this. They're not very expensive and can make a tremendous difference to the amount of noise that's generated. Now, the last thing to do is to set up that backup disk and then create a routine job that we can use to back up our data from our NAS onto that backup disk at regular intervals. I'm going to set mine up weekly, so I'll show you how to set that up now. So the first thing we need to do is actually format our backup disk. And now we've got that done, I can now create a directory to mount it into and then mount it. And now you can see that both our NAS directory and our backup directory are both mounted. The next thing I want to do is set up a script that I can use to create periodic backups. All this script does is call the rsync command again to back up anything that exists under /mnt/NAS and then copy that to /mnt/backup. It will do this recursively, and it will also copy only stuff that's new. So the first time we run it, it will copy over everything, but after this, it'll only copy anything that's changed. Now, one thing to bear in mind here is that if you delete anything under /mnt/NAS, those files will still exist under /mnt/backup. Next time the backup script is run, it won't delete them from there. Now, this is a really good thing because if you accidentally delete something, at least you'll have your backup of it that you can restore. However, if you are worried about disk space at any point, you'll have to go in and clear out any files that you intentionally deleted from your backup drive. Now, all we need to do is change the permissions on it. And now let's run it and see what happens. And there you see it's completed. Now the command gave no output, so we actually have to do something else to see the log messages that got written. We can do that with the journalctl command. If we scroll this all the way to the bottom, then we can see these messages here, and this was the output of our backup job. And here you can see that it's copied both of the files that were there in our NAS directory off to our backup drive, and we can prove that by looking at our backup directory. So now all that's left to do is actually run this on a schedule, and we can do this using cron. All we have to do is create a file under /etc/cron.d to form our job. Now the first bit of data that we need to put in here is the minute at which we want our cron job to run. In this case, I actually want it to run at 1 AM every Sunday, so I'm going to set the minute to 0. Then I'm going to set the hour to 1, so this represents 1 AM. The next parameter represents which day of a month that you want to run it. And I'm going to say star for that, because I don't care what day of the month this runs on, I just want it to run every Sunday. The next parameter is specifying the month that you want it to run, and again I want it to run in all months, so I'm just going to provide a star there. And then the next parameter represents the day of the week that you want it to run on. Now this starts at 0 for a Sunday and goes through to 6 for a Saturday. So since I want this to always run at 1 AM on a Sunday, I just have to put in 0 here. I then have to put in the name of the user that I want the job to run as, in this case root. And then finally the name of the script that I want to run. And then I just have to save this out. And that will then just set up that job to run every single Sunday. The last thing we have to do here is set up what's called the automount file in order for our NAS drive and our backup drive to be mounted at boot time. In order to do this, we need to edit the /etc/fstab file. And here I just want to add a couple of lines to the end. The first one is to mount our NAS drive. Here we say we want the device /dev/md127, which is our RAID 5 volume, to be mounted at /mnt/NAS, and that it's using the ext4 file system. It's applying all defaults to that. All of the rest are just parameters to the mount system. And now we do a similar thing for our backup drive. And then this will specify taking our backup drive, mounting it into /mnt/backup, again specifying the file system and all other parameters. When that's done, we can just save this out. Now we've made a change to the fstab file, we need to actually reload that into systemctl. And now that's done, we can reboot. And now here we are rebooted, and if I run df-k, you can see that both our NAS and our backup drives are now automatically mounted. And so there you go, your very own NAS built around a Raspberry Pi 5. And that's it for this video. Once again, if you liked what you see here, please hit that like button, subscribe if you want to see more, and also hit that notification bell so you can be told when I put a new video out. Let me know in the comments how you get on with this project. And also let me know in there if you've got any other ideas for projects that you'd like to see me do. Thanks so much for watching till the end, and until next time, bye for now.